Some reactions, some processes are spontaneous, and I think we talked about this a little bit at the beginning of the quarter. Spontaneous processes happen by themselves without adding energy. Once they started, they just go forward. And so the example here in this picture is that once you start that ball rolling down the hill, it's going to drop. Now you may have to initiate it, right? You see that he tips it up over that bump. So he initiates the process, but once it starts falling, it goes continuously. However, going in the opposite direction, rolling that ball up the hill takes a constant input of energy. And so that is a non-spontaneous process. And whether something goes in the forward direction or not is independent of how fast it goes. So some things are very fast, some things are very slow, and that's kind of a separate issue. We'll take a look at kinetics a little bit. Which of the following of these are spontaneous at room temperature? A drop of food coloring spreads in a glass of water. Yeah, that's going to happen all by itself. As soon as you put it in there, it's going to spread out. What about methane burning in air? Yeah, once it starts, you have to light that spark, but once you start the spark, then it just goes. What about water freezing into ice? Not at room temperature. Now, if we put it in a cold temperature, yes, then it will go in spontaneously. So temperature does have a role to play here. What about iron rusting, like in this picture?
So for C, is it spontaneous or not spontaneous?
It's not spontaneous at room temperature, but rusting is. Spontaneous means that it will happen all by itself. So at 25 degrees C, we could have water solid is going to turn into liquid, right? This is the ice, and then the water is melting. Freezing is the opposite. So at 25 degrees, it's not spontaneous. So we're going to talk a little bit about how fast reactions happen, and we did talk about a little bit of this at the beginning in terms of collisions. So now we're going to weave in that idea of the collisions relating to the rate of the reaction. How fast can it go from reactants to products? When the reaction happens, they have to have enough energy to break a bond. And only if they have enough energy to break the bond can they form a new, different bond. And there's another couple things that have to happen. Now, if it has a collision and the bond doesn't break, then they just bounce off. No reaction. But if the bond breaks, then maybe it can reform the same bond, or maybe it can switch atoms. So you see in this picture, they're lined up in a way that they can form two new atoms here. That orientation is an important part. Molecules must collide in order to react, and the more often they collide, the more likely they'll have enough energy to break the bond. So we can increase the number of collisions by increasing the concentration, how many particles are in the solution. If there's more concentration, then they find each other sooner. If we increase the temperature, then they're moving faster, and that has two different ways that can increase the rate. One of those is that when they have a collision, there's more energy. They're moving faster, so there's more energy. More energy because they're moving faster. And because they're moving faster, they find each other faster. So they meet other molecules faster because they're just covering more space. Okay, so which will have more collisions? N2 at 25 degrees or N2 at 100 degrees?
100.
Yeah. You could think about if we were all together in the same room and I said, okay, everybody get up and we're going to walk around, and we walk slowly. Then there's time to be careful. We don't trip over the desks. If I said, okay, everybody run really fast, we're going to have more bumping. We're going to trip over the other objects in the room. When we're moving faster, there's going to be more collisions. And this is going to come into our lab in 1 week.